Alright, thanks for having me here. It's a pleasure to be in Japan. So, my talk is talking about implementing custom integrated circuits, challenges, innovations, and open source solutions. The past 4 years I've been involved in a new initiative that aims to enable chip design. It started with the Idea Dharma program, and where I worked on projects at Grenoble and M.Sc. And then this kind of Google open source initiative where I worked closely with them on, along with partners like NIST, to take some of the hardware design methodologies and optimize the chip design. The overarching theme here of this talk is to accelerate chip design. The way to do it, obviously, is by lowering costs of chip design. But the current status quo of the chip industry is limited, and we have to go through a bit of history to understand what's going on. So let's take an example of the software development in the 90s. This is what it looked like. We had enhanced compilers, lots of mechanical activities, and the lack of stabilization, so everything was Relics of the 90s is a common way to refer to these absurd issues we had back then. There's a whole bunch of so, but more seriously, this reminds us of something today. To me, it definitely looks like hardware development today. But of course, we have much more computing power, and we can do much more stuff like that. But in general, the semiconductor companies have in-house tools, tool chains that actually turn into require to be separate to extend data formats, as well as support tools of everybody and support exactly. As a matter of fact, I'd like to survey our new students and ask them to describe their tape-out experience, and usually in an older note, using one word. The result isn't great. Usually 50% is negative, and the other third is neutral. Now imagine if you ask new generations of students that are already a software-oriented mindset, might have less motivation to send and debug why the tool is crashing after a 24-hour lesson without actually being able to look into the source code or have the IT department to produce the problem. I'm not sure if this would make still chip design exciting for new generations. So the common feedback we're getting is I'm liking the tools rather than I'm learning how to do chip design. And that's a real problem. At one of the major tech companies, where they have an army of software engineers, the ratio to hardware engineers is very balanced, which is actually very symptomatic of the overall US workforce and also new student career choices. Based on the Career Explorer website, there are currently estimated of 70,000 hardware engineers versus 830 software engineers. So there's a ratio of 10. And the same number is expected to grow by 30% for the software engineers versus 5% in 1 decade for hardware engineers. So there's a real imbalance there. So the idea here is to find ways of turning software engineers into hardware engineers, hardware-friendly engineers. To give you a more tangible example of my idea here, last summer, Ali, who's an undergrad, he's 19 years old, from the computer engineering department, reached out to me and asked to do some work over the summer. And he started playing with the tools with our framework of M.Sc. And then 6 months later, he was among the winners at SSCS, which is the flagship conference. And he won his scholarship notebook competition and presented his work on M.Sc. That's a great demonstration of having more software-minded students, hardware and software. As companies like Google, software development is fast, it is within hours, which means development of new product is within weeks. While in IC design, it is well accepted to talk about months and years without even mentioning the risk and cost of technical chip. Now, of course, there are time constraints, time constraints for chip design, which is really hard to change. But looking back at my comparison to the software in the 90s, there's definitely room of improvement to our methodologies and practices in hardware. In fact, if we talk to our software colleagues and even to our EDA friends, which is even a smaller community, it sounds like hardware development is broken. That's how they feel about it. Is this the case though? The answer is no. We still build very complicated chips, but can we do better? Yes, I think it is about time to start fighting windmills and prioritize designs. Now another angle here is cost, right? Chips are very expensive to make. What we really need to understand is when it comes to fabricating a new chip, the cost of building up a new integrated circuit from scratch at the wafer level can be very high. So I'm talking here about licensing IP is expensive, paying for custom design is expensive. EDA software can be very costly as well. And tape-out massive costs also vary widely from tens of thousands to millions of dollars depending on technology nodes. In 2020, with my co-author Tim from Google, we published this work about enabling open design. We released with the release of an open source PDK and our work on EDA tooling like Grenoble. The stage was set to build to have an innovative way of designing and building open source ecosystem. On my side, I have started working on a corollary of FSR, which is a DARPA project, and I started calling it OpenFSR, which was available to everyone to use. In the plenary session at SSCS in 2023, basically building a chip from 65 to 5 nanometer plus 18 times more. We're talking about $500,000,000 to build a chip that's 5 nanometer. And that's very important for you, right? So having an open source enablement is unheard of, and it will help us organize our software practices in OpenFSR. Through open collaboration, we use design space exploration, CI, and by adopting cloud and software practices in hardware. So I'll get to that here in this presentation. So one way of driving down the cost is by encouraging automation. In our research, and in Michigan, we work on a proposed framework called FSR, which is one of the DARPA IDEA program and allows us to automate database models. So I made here a very simple workflow diagram on the left of what would be traditional analog data data. As you all know, most of it is custom, requires multiple iteration from schematic to layout and so forth, and sometimes require more information. So the idea here is to basically So the idea here is to basically take what would otherwise be fully custom analog layout and shoehorn it into a cell-based approach, which is very amenable to the digital flow. So as you may know, that like the digital flow or the grid-based flow is highly automated for right now. So the idea is to basically take what would otherwise be custom design and run it to the digital flow. I'll explain how to do that. The framework is very similar to any digital flow. It uses a lot of Python in it, closed tools or open source tools. So you've heard it a few times now. We use a cell-based approach and general design. But what is it exactly? A simple way to understand this is that we try to describe blocks in Verilog and structural Verilog behavior. So we'll plug in some specific cells we try to be electrical auxiliary cells, which I highlighted here in blue. And they are very small circuits, below 12 transistors. So now, usually these cells are usually a fine cap switch or unit cap or comparator. So they are very easy to build from scratch and allows you a lot of flexibility when you build a new topology. So I'm showing here some of the layout in Global Foundry 12 nanometer, and we have been able to do this in closed tools, but also through the open program, we're able to create OpenFSR and use the open source tools. So in summary, this is an overview of what we did in the FSR project. It is a DARPA program. It is a Utah University and industry effort led by the University of Michigan. And FSR specializes in autonomous SoC synthesis, which includes all the building blocks, such as analog memories and tools. Over the course of the program, we have been able to successfully take out a good number of SoCs as well as test chips. I'm showing here two SOCs we have been able to demonstrate at Salt Lake City ERI Summit run by DARPA in 65, and it was a great success. Since then, we have ordered our generators to TF12, Skyward 130, and so on. So here we're discussing about the generators. So we're able to generate, for some reason, jump in. So now that the IDEA program is over, the FaceOff project is a graduated project, and we have been able to completely do the data program. But now we started the FaceOff project, which is funded by multiple partners such as Google, KDA Tanker, and STMicroelectronics. We also have in-kind funding through global foundries, Intel Foundry Services, and Skywater, and we've been able to crank out a multiple tape-out over 2 years with less than 10 people using this open source tools. We're also endorsed by the Chip Science and the Linux Foundation, where I'm running or chairing the anode working group, and where we discuss on how to automate anode design. Now, since we looked at the OpenFSR framework and how we leverage digital flow to perform the anode layout, in the next slide, I would like to explain a little bit of the trade-offs, right? So how do we do that? A good example for regulation, we use the digital flow, we create the auxiliary cells, and we do a place and route to get our designs. Now, the first version of our framework is using predictable placement. So if you look at the pre-parasitic netlist, we have a smooth curve that looks very nice. But then if you go to post-parasitic extraction and you run the simulation, you end up with a lot of variations, and load current is taken at all. So this isn't a really great design. So how do we resolve that, right? So we came up with a structured placement, which is really easy using Python, but also we started using a technology parsing, where we go and check the technology level, check the sizing and metal layers, and we started calculating power mesh so we can reduce these variations and have multi-categories, large routing, and so on. So we were able to resolve this problem. This is just an example to give you a sense of how it's going to work. So I really like this diagram here, which summarizes where FSR, which uses both commercial tools and open source tools. So if you take a full custom design, which is all the way to the left, which has 100% complexity, and compared to the initial version of FSR 1.0, which we started 4 years ago, or 5 years ago, which requires minimal constraints without any custom placement. Obviously the complexity goes way down, but performance is very bad, right? Now, if you go to the left and you put 100% constraint, you took all the PDK, DRC rules, and all the complexity of generating a layout in the technology, you end up not having a generator if you're actually creating a layout using code, which is even more complicated than with layout. So in fact, in our cell-based approach, or digital approach, we are in reality avoiding extreme complexity. We're trying to take in all the PDK DRC rules that comes in with full custom automated layout, like routing or active layer drawing. And that gets really complicated as we go in advanced node like FigFed and so on. Also, with the rule of diminishing returns, the time required for to a new PDK or even a new design topology would essentially make automated full custom anode generator too costly to make across PDKs and cases. And we've seen that with some of the generators out there. So now I want to run you through a couple of projects we're doing which I think are exciting. First of all, I'll start with the fully open source project we started. We weren't really targeting anything, we just wanted to build confidence in these tools. So the first thing I want to highlight here is that this was a big bang event with the open source PDK. We had tenants of driving this with evaporators and so on, and we had the Skyward 130 PDK. Then we have the second version, or second PDK, 180 Global Foundry, which is a bigger foundry, and then we have IHP and so on, and maybe we'll have more PDKs in the future. As you can see, I just want to highlight here that we started with a small number of tape outs, and as we went through time, we had like hundreds and hundreds of tape outs, which is really exciting to see, and you can see that confidence has been built in these tools and approaches. Now, coming back to the benefit side, we were able to tape out and crank out this first tape out. This was done in a month, and we were able to tape out 64 sensors. The reason we were able to do it in a month is because the framework was there, and we were basically just porting everything to open source tools. So these are multiple BTs or flavors of the sensor, and we use a low power leakage based digital sensor, which used as a template for the generator framework, which is based on a design published at ISCC 2016. The sensing element, which is the rim oscillator here, is at subthreshold and employ leakage-based temperature dependency, where the temperature is inversely proportional to the natural numerical oscillator. So we tried out a couple of things. We tried high power for lower quantization noise, and so on. So we had multiple versions. Some of them had higher power and better inaccuracy, and lower power but smaller size and so on. We were able to test these chips. This was one of the first functioning chips in the open source ecosystem. And using our framework, you can see we can have a lot of data that trades off the inaccuracy versus the power, resolution, time conversion, and we can start getting some cluster of data that's very useful for foundries to do design-based exploration. So again, for inaccuracy, we're able to hit below 1 degree C for low power and cheap design. And we have multiple versions. This wasn't really optimized, but these are state-of-the-art numbers, and we were able to get a high speed versus a high density design. This design was published at the Solid State Circuit Letters, which is a beautiful venue to publish this work, and we were able to compare to, we made this table as a comparison to the other works using 2-point calibration. So you guys can go and check this paper if you need more information. On the second shuttle, back in 2021, which is a while back now, we were able to do the second tape out, which was using first AMS SoC, and we were able to do the same exercise, but this time with 10 LDOs and a processor. We aren't able to test this chip correctly for some testing issues we had with Carbon, but hopefully we were able to simulate it and show some good numbers there. And this work can be used in the future program shuttles. So this is the DLDOs. Again, we're using the cell-based approach. And the cool thing about it, I would like you to understand here, if you take the red cells here, those are the auxiliary cells, and you can replace them. You can make multiple variants. And if you make multiple variants, that means you can have multiple versions of your design. So what we did here, in Grenoble, there's a native transistor which you use for power as a power switch, but you can use a PMOS, right? Or you can use different sizing. And that gives you a wide range of designs that were generated that you can use. We also made a voltage regulator or voltage reference generator and a min-cap array, and we fenced the power transistor arrays as well, so that we can have reduce the variability in the design. Again, this was integrated with the OpenTitan core. Titan is a root of trust. This was the first version we taped out. We didn't have full control of it, so we made a very simple version of it using UART, SPI, 16 KB, SRAM, and so on. And the idea here is basically to build confidence in these tools. And I want to stress that out because we come from a far away, and we've been able to improve these tools as we went to the years. So I'll show you that in the next slide. Now, the next project that I think is very exciting is the NIST Nanofabrication Accelerator. This program is run by Dr. Brian Hoskins from NIST, and this is the first open nanotechnology platform. So this work started with the partnership between NIST and Google. So we worked under this umbrella here. We partnered with NIST so that we could start making test structures for liquor characterization recharacterization of the sky water PDK at room temperature, but also at cryogenic temperature. So this is actually unheard of, right? Having open models at 4K for quantum design and so on. The other thing we started is generating these test structures for creating new models, compact models. And I'll go into it later in this presentation. So why do we do this? Because NIST requires a lot of test vehicles to accelerate nanofabrication research or science, basically. And as such, NIST and the nanofabrication community are extensively benefiting from this. We're basically characterizing new devices like the RM, PCM, spin torque transfer devices, nanotubes, 2D materials, and so on. And all this can be co-integrated with CMOS, and you can characterize it with lower parasitics. So the aim of this project is to put some test apparatus on the silicon, which will be used as a carrier wafer to characterize immersion and memory devices. So that was the sketch of this project. Now we started with the multiple tape-outs, and this is the idea. We have drastically reduced the parasitics, and we improve the SNR. We have on-chip signal generators, integrated amplifiers, and so on. The first tape-out was very simple. We needed very simple DC circuit test structures. So we're talking about here MOSFET arrays, precision resistors, line resistance, VR resistance. But the problem we had with OpenFA SOC is we weren't able to generate customized design. So we're using a cell-based approach, and that means we had to do the layout manually. But then, as we started working with this project and having available all the tools in the open, like GDS Factory, which is actually one of the moonshot factory from Grenoble, we basically made this framework for photonics design, and we leveraged that work there to make ASICs. So the first test structures are ring oscillators, intermediate ring oscillators. So what we did is use OpenRoad, which is the basic tools, and we started doing Python manipulation of the design so we can have this customized placement. So this was really along our strengths, and we were able to do it, and it was very easy. So we cranked out multiple chips, multiple ring oscillators, and NIST was really excited about it. But what we started doing, and it's very interesting here, we started making these customized cells, right? So we can arrays, diagonal arrays, line resistance, which like a snake protein, and those are very interesting layout features that you can use for another layout. So as we started coding that, we started making these APIs that basically takes X and Y dimensions and pictures and layers, and it dumps an array in the caps. So that's very useful for applying caps, for instance, for a DC-DC converter, right? And so on. Iteratively, we started making these APIs that we can reuse across different technologies, but also generators. And we were able to put everything within the pads that which are very relevant for so overall, the process of generating the link cap test structures or diode test structures boils down to a few steps. Using the APIs to compute and place the small capacitors on the grid, generating the connecting mesh metals, and replicating the structures as needed. So when you have these APIs available, you can just use them and you can get a lot of things done. So by the end of the tape-out, which took 2 months by the way, we were able to crank out 1,400 pads for 400 plus transistors and so on. This wasn't heard of by NIST, so they were pretty excited about our framework. But that didn't end up there. So we did MPW5. Please remember here we have 3 months between each tape-out. So we were able to do MPW5, MPW6, 7, and 8. As you can see, the test structures are getting more complicated. We have the PMU, we have BCOs, LC tanks, RM devices, and so on. So this was like a very good demonstrator of what we were able to do with NIST and digging into these new structures. Finally, this is the pyramid. Here we showcase what can be done at a range of applications, along with the physicists collaborating with NIST. And other industrial partners. We are creating an open source stack with regular structures where every part is open source, from the software all the top or way down to the silicon at the bottom. Critically, the silicon at the bottom can be introduced into any university fab and used to benchmark electronics memory devices. So this is only one project, but we are actually creating multiple test vehicles to characterize these emerging technologies. So now, coming back to the performance versus tool complexity trade-off that I showed you earlier, with these open source tools, we are able to have more control over what we're doing. We're actually adopting more software practices, and we're having a lot of software engineers out there that could help us and show us how to do things in a better way. You know, traditionally, circuit design was very closed, so we weren't having a lot of feedback on how to do things. And now with the open ecosystem, we're able to discuss with many people and basically improve our framework and you know, encourage reuse and you know, software practices in our hardware. So this is a current project we're working on. We're actually moving towards more programmatic layout, and the reason is we're working on this nanofabrication accelerator program, but we're also working on back sensing and so on, and this requires very, very high precision analog, like low noise and low power and so on. So, and also, some of the blocks we're using, like the auxiliary cells, require customized layout, but we need TIAs, amplifiers, and we need direct control over the layout. So we started looking into more of the programmatic approach, and we're making this framework where this is an example of an auto-generated comparator cell we developed in our group. What we're trying to address this by using GDS Factory and Python-based scripting. GDS Factory provides a framework for programmatically building layouts with object-oriented code. The main advantage is to keep cell software generation independent of the PDK. So actually this cell here is in Skyward 113, but if you change the PDK, which is a class, you can actually generate the same layout to GF118. So we tested this and we're actually building over and over bottom-up these generators. The generators are implemented as Python functions, which return full layout stored in GDS Factory component types. These functions can accept arguments for automatic customization. The generators can also call other generators to produce hierarchical design. The user interface with the generators is a Python package. The user imports the PDK package and the target generator. Then in one line of code, they can create a full layout. With the programmatic generators, we can achieve quick creation of layout from Python's functions, enabling reuse across the designs. With varying design parameters here, we are actually automatically generating a current window with various stages, shown here. So this is very cool because we can make this LNAs, right, for cryogenic temperature design or CMOS. Right? This is another project with NIST. One of the main applications for cryoconversion is to build the control system to interface with quantum processes. And to do so, the control needs to sit at around 1 to 4 kelvins. Another consideration is power. The emission phase has a limited cooling power, so as we go down in temperature, so meaning we have to control, the control system needs to be within milliwatts in terms of power budget. So we have achieved some initial results, including the release of prior models in Skyward 113, and we're publishing a work with the full cabin list in ICTS this year. Together with these partners here, we have developed test trials and we tested them and we created the compact models that can be used for design circuits. One of the most interesting designs here we built in GF12 using our FSOC generator. This is a recursive SAR DC-DC converter based PMU, which we generated using our FSOC framework. This was tested by NIST at their locals using their distribution footage. And we were able to test it from 400 Kelvin down to 20 Kelvin. We weren't able to go down to 4 Kelvin for some instrumentation problems. But we can see here that we are around 80% efficiency across the whole range of temperature. That's pretty exciting, right? Because the reason here is because we're using a bootstrap switch, and the bootstrap switch is an auxiliary cell. So if you want to do this if you need to do this for different application, the switch can be changed for whatever you're targeting, and you can change the efficiency, the setting time, the power, and so on. Now, our framework allows to do rapid prototyping. So in Michigan, we are specializing in power design. There's a project called Millimeter Cube, where we have around nanowatts of standby power, right? So I think it was obvious for us to create some of these blocks for low power IC design. So this is one of our projects we did with Fujitsu 55 EEC technology. This work was published at ISSCC 2019 and JSSCC 2020, and it uses body biasing. So it requires multiple charge pumps. So in this project, we have at least 5 charge pumps to limit the power. It's using a Cortex M0. This is all using commercial closed tools, but it just shows you an example of what can be done. This is the chip. This is one of the best state-of-the-art members in terms of energy efficiency. We achieved 6.4 picojoule per cycle, including the PMU and the power management. Why I'm mentioning this, the reason is because Fitbit reached out to us and they want to create low power circuits using our OpenFA software. So, and as we started this collaboration, we created our front end, which is basically a lab on a chip concept. And we taped out this is Grenoble 130, it's using APCs, DACs, and DACs. Again, 3 months later, we did another tape out in GF180. This is what, with 10 students, we were able to crank out all these chips. And again, we didn't use a generative approach here, but we used a lot of the layout and the methodologies we're using for Skyward 130, and we were able to tape out this chip here, GF180. Now, the other angle of my talk here is hardware security, and we're building through some funding from SRC, the first open root of trust SoC out there. We're using OpenTitan, which is an open source generator for root of trust, which includes multiple blocks like the CS RNG, the OpenTitan big number accelerator, and the EDN, and so on. And this helps for your security and accessing your servers and so on. The issue to make the root of trust diagram on the left fully auditable and transparent, we propose to use our expertise in both the open source CDA, toolchain, and IC design combined with OpenFA software. We have been able to develop multiple silicon validated IPs, and we plan to extend this work for true random number generators. We're using actually ARM-based true random number generators, which are pretty rare out there. We're proposing a couple of countermeasures to mitigate side channel attacks, such as voltage domain stacking, which I believe could minimize the power signatures of the AES accelerator. We're also developing a new secure programmable PMU, which underscores the flexibility and broad applicability of the OpenFA software approach. The PMU is using an OpenFA substar generator approach, and we created security primitives such as ARM-based generators. This is, we did actually an experiment here. We already created the stack voltage domain, so actually there's 2 voltage domains on top of each other, and the lower voltage domain is actually using glue logic, so the accelerator is sitting there and it can run subthreshold voltage. So I'm going to show it here, and we included noise injection in these blocks, and the higher voltage domain has all the analog blocks like the PMU and the memory caches and all, which are not very amenable to scaling the voltage. This is the PMU. It's using a SAR DC-DC converter. We're using a noise injection block. This was taped out in Intel 16 just recently, and I'll show that later in this presentation. Again, for the ARM device, we're trying to use a compound of noise. We're using telegraph noise, but also there's a new, a really interesting noise that is in RM for resistive memories, which is called quantum noise, which we're trying to capture or sense with the structure I'm showing below. So all of this is using open source tools, by the way. So now, the next part of my talk here is to talk about how we're trying to build confidence in this open source tools. As I said, we started at the end of 2020. We did the first tape out. We were able to show that this temp sensor was working. There's a lot of results out there, and the chips are available. The silicon results are on GitHub. Then we did the second tape out. We don't have the silicon data for it because of the Grenoble issue we had, but we are able to simulate it, and we're pretty sure this is functioning. We can get a lot of data out of it, and it's something very important for us, database optimization. We are able now, without having the need for a license and having a cloud-based infrastructure, to run this simulation across different range of applications. So we can trade off here the pre-pull, settling time, overshoot, undershoot, and so on. And we also started looking into feedback tape-out. So through the DARPA program, we had access to GF12 fellow. So that's very cool. We were able to create a BLE transmitter that's using an ADPLL and a switch cap-based power amplifier. But we also taped out the first version of the OpenTitan in GF12, which is actually 250 megahertz. And we also included some of the temp sensor there, so the sensor post-specs is actually below 0.2 degree in accuracy. So that was pretty cool. So again, on this timeline, we are doing the tape-out for the nanofabrication accelerator tape-out. We taped out already 4 chips, and in 2 weeks we're going to be taping out the final wafer, which everyone can use. So please reach out if you're interested in this project. And again, feel free to reach out to us. We did these 2 tape-outs in Skyward 130 and GF 180, and we're still working on other tape-outs with these guys. The Intel foundry reached out to us. We started using this Charlie multiple tape-out. We started with the first one in 2016. We taped out the array sensors, OpenTitan, but we also made the 2.8 time interleaved ADC and the quantum current standard circuit for this. The last tape out we did is a final root of trust that I'll show very quickly in the next slides. The OpenTitan SoC here, we taped out in 2016. This is using OpenRoad, and we try to fill in the gaps using comparative tools for verification and so on. But this is basically pushing a little bit more against Skyward 130 and GF 180 and do more complicated technologies. This is the temp sensor. So the exciting part here I want to highlight is this sensor is being using OpenFSR framework. Is using a full end-to-end open source toolchain. So we don't need any commercial closed tools here except for verification. And this is the last part of it. This was the final version of our OpenTitan framework. We're still planning to do a tape-out in November this year, but we included the PLL, TRGs, noise injection block, flash, ROM, and all. So this is getting really close to what we will do with commercial tools in our group. So what is next? This slide here is from Google. I really like it. The goal here is to make custom silicon easier to build at scale, just like software. I really love this slide here, and this is our goal. Using things that are being developed by Google, like Conda packaging, you can basically do Conda install, and you have everything, all the toolchain out there. That's very, enabling for new designers, and I can see that within my groups with undergrads. Again, one thing that is very interesting here is the reusability of results, and we use these concepts that are unknown in our field in semiconductor. But now with all this infrastructure available out there, we can reproduce results from different countries, different groups, and different expertise. OpenFSR is actually mainly code and documentation. I just gave you here a sense of what it is. So we're actually not working with schematics, we're working with code. OpenFSR is auditable and transparent, so no malicious tampering, and everything is automatically generated. There's regression tests, there's systematic matrix extraction, dashboards, and so on. So a lot of things can be improved, but this is what we're trying to build so far. And finally, our goal here as a faculty in Michigan is to bridge the gap between hardware and software. So I'm trying to blur the lines between these two and use this expertise from EDA, analog, RF circuits, and software. So in our department, I'm trying to get more students from the CS department getting involved in circuits. And the only way to do that is through abstraction. you cannot ask the software engineers from the CS department to work with the transistor. But if you abstract that, he's able to build using bricks a full system. Finally, I want to talk a little bit of what we do at the Solid State Circuit Society. So with Boris Mervin, who's chairing our committee, we are running this Chipathon. So this year actually we have people from Japan, and this program is running to 6 months. So we started in 2021. We had 61 submissions, 18 were selected, and we had 11 takeout. In 2022 we have a little bit less than that, but we have a better quality of designs and more groups that are actually circuit designers joining us. So we did 14 takeout by the end of that. And these are examples of the projects. You can see people from Brazil. So these are places which didn't do really takeouts before or are not known to be doing takeouts. But we had people from Pakistan, strongly Egypt, and Chile. Again, for the second Chipathon, we had multiple other people. Designs are getting more complex and more exciting. So all of these are really exciting to be seen. But finally, this 2023, we came up with this new concept, which is a lab on a chip. People, when they take out their chips, are not able to test it in Chile or Pakistan. So they need a lab on a chip so they can get around the testing equipment they require. So with Boris, we came up with this concept here called lab on a chip. And we can have actually oscilloscope macros within your chip so we can test your design. Another thing we try to run is this called a chip competition. We started in ISSCS in 2023. We had 7 winners from China, Japan, actually from this university, Chile, and so on. And they got their prize at ISSCC in not the plenary session, but one of the events, travel grant event. Again, we have the same competition at Mehdi. We had 3 winners, but one of the designs I want to highlight here that shows basically what we're trying to do is a design optimization of analog digital LDO, which is using a reinforcement learning. So this is the type of work we would like to encourage in our community. So with Boris, we run the competition. There were 3 winners. It happened at Kyoto last week, and we're planning to have more of these events at ISSC 2024 and Mehdi at Hawaii next year. We also started looking for venues for this software, this open source work. It's very hard to get into ISSCC, CRCC, and Mehdi. So the idea, we tried to work with ISCAS, and I chaired this session here where we had a review of the first silicon result on open source ecosystem. So that was at ISCAS this year, and we plan to have more of these venues and give people more opportunity to publish their work. And finally, one thing that was really exciting to see last week is the workshop on open source design, where we had around record attendance actually among all the other BSI before, which was around 180 attendance. So that was really exciting for the SSCS to see how many people are interested in open source design and how we can encourage people to work that. So I think this is really exciting. I will see more of it as we go. So thank you, that was my talk, and thank you guys for your time.